Hello everyone and welcome back again to the linear algebra component of the calculus and linear algebra series. In the last video we outlined how to construct an indirect proof. So recall that went of the form that if I was given a particular statement and I modified that statement into an equivalent statement using the equivalences that we've shown in the propositional logic section, if I can prove the equivalent statement, then I will indirectly prove the original statement. So that is what is known as an indirect proof. And we showed how that was useful for constructing kind of proofs by contradiction in the last video. And in this video, what I want to look at now is I want to look at how we're going to construct indirect proofs using this equivalence that we did in the propositional logic section that was the contrapositive equivalence. So recall that was that if I was given a statement of the form P implies Q, because P implies Q is equivalent to not Q implies not P, it suffices to in fact prove the truth of not Q implies not P, and that will in turn prove the truth of P implies Q. So let's see how that works with some examples here. And the first example that I'm going to consider is going to be one that we've actually already seen before, which is to say that if n squared is even, which we write here if 2 divides n squared, then 2 divides n, that is that n is even. And we proved this actually in the last video, but we did it by a proof by contradiction, so it's still an indirect proof the way we should do it. And in this video what we're going to do is we're going to prove it by contrapositive, and this also outlines that you can prove statements in many different ways. There isn't one preferred way of proving a particular statement, so you can try many different proof techniques, and different proof techniques might work on the same statement, so it's worth trying lots of different things. So how would we start to prove this by contrapositive? Well, we've got a statement of the form P implies Q, and we start by supposing that the thing on the right hand side, that is this Q, is not true. That is, let's assume that 2 does not divide n. So we start with that statement. And if we can show as a result of that, that 2 does not divide n squared, then we're done. So what does it mean if 2 does not divide n? Well, it follows then that n is odd. And because n is odd, we can just say that it can be written as 2k minus 1 for some k in the naturals. In other words, it's 1 away from some number divisible by 2. Now we can just do some simple algebra. We can square n. Squaring n gives this expression. And we see here this is just another number that is 1 away from a number divisible by 2. In other words, n squared is odd. So we've shown that 2 does not divide n squared either, and hence therefore we've shown the contrapositive is true, and by the equivalence of the contrapositive and the implication statement, we've proven the original statement indirectly via this proof by contrapositive. So that's exactly how we would prove something of the form P implies Q indirectly using this contrapositive equivalence. So let's look at another example here. And our kind of next example is going to look very similar to the previous one, kind of identical in every way apart from now we're considering 3 rather than 2. So we've got that if 3 divides n squared, then 3 divides n. I'm also considering this example because you'll see in this example that we're going to kind of compound it with another type of proof technique, which actually was in the direct proof section, which is otherwise known as a proof by exhaustion. So what we'll see is we'll start by proving it by contrapositive, and we'll also use a proof by exhaustion to kind of prove the proof by contrapositive. And it shows that in fact you can compound many different proof techniques into a single proof. So let's start off. We assume that the thing on the right hand side of the implication is not true. Let's assume that 3 does not divide n. Well, what does it mean if 3 does not divide n? Well, then the only two possible cases, which is where the exhaustion kind of proof is coming in, is that either the number is 1 away from something divisible by 3 or 2 away from something divisible by 3. So in other words, we can say n is equal to 3k minus 1 for some k in the naturals or 3k minus 2 for some k in the naturals. And now that all the cases exhausted, let's square both of those cases, show that the squares are also not divisible by 3, and therefore we will have proven the contrapositive and in turn proven the original statement indirectly. So starting with 3k minus 1, when we square that expression, we see we get something like this after some simple algebra. In other words, we see we get a number that is 1 away from something divisible by 3. In other words, it's not divisible by 3. That is, n squared is not divisible by 3 in this case. And in the other case, again by some simple algebra, what do we see? We see here that we get something of the form 3 brackets k squared minus 6k plus 4. In other words, it's 4 away from a number divisible by 3, or 1 away from a number divisible by 3. And therefore we conclude that in that case, n squared is also not divisible by 3. So in either case, in both cases, we've concluded that 3 does not divide n squared, and hence therefore we've proven the contrapositive. We've proven the contrapositive is true, and we finished our proof, so we put our nice square box at the end to say that we've proven the contrapositive, and therefore we've indirectly proven the original statement via the equivalence in the propositional logic section. Now the final thing that I want to address in this video is something that's slightly different from direct and indirect proofs. They don't kind of really fit into those categories kind of straight away. It's a different way of separating proofs, and this is known as a constructive or non-constructive proof. So suppose I'm given a statement of the form something like there exists x p of x. How would I go about proving that statement? Well, what I need to do is I need to find a value of x for which p of x is true. So a constructive proof would go along the line that I explicitly find the value of x in the domain of discourse and show for that value that it satisfies the condition p of x. Right, so that would be a constructive proof, but I could also do a non-constructive proof. I could still prove that that statement is true without actually finding an explicit value of x. In other words, I can just say I know there is a value. I can prove that there is a value that that exists, and I know it will satisfy that condition, those conditions, but I don't explicitly tell you what that value is, and that's an example of a non-constructive proof. So let's see that in this particular example here. And the statement that we're going to try and prove is we've got there exists irrational numbers p and q in the reals such that p to the power of q is rational. So let's start with a constructive proof. Well, a constructive proof will go in the form that we need to find values of p and q that are irrational and show that when we raise them to the powers of each other that we get a rational number. So what I claim here is that these two values, namely p is the square root of 2 and q is log to base 2 of 9, exactly satisfy that property. So we know p is irrational because we've proven that in a previous video. We don't yet know that q is irrational, but let's see if we do p to the power of q that we get a rational number. So some simple algebra now, and just going through some rules of logs and exponentials, we can conclude that if we do p to the power of q, that we actually get 3 out, right? And we obviously know 3 is a rational number. That is an element of the rationals. So all we need to do now is we just need to show that log to base 2 is irrational. If we can show that log to base 2 is irrational, then we're finished, because we know that the square root of 2 is irrational, and if we show log to base 2 of 9 is irrational, then we've concluded that we've got two rational numbers that we raise to a power and is equal to a rational number. So how would we prove that it's irrational? Well, much like we did with proving the square root of 2 is irrational, let's suppose that log to base 2 of 9 is rational. In other words, we can say here, suppose towards a contradiction that a log to base 2 is rational, so we can write it as a over b, where a over b are defined based on the set of the rational numbers. In other words, a is an integer and b is a natural number. So doing again some simple algebra and kind of taking that exponential to the other side, we can get this expression that we get, then it follows that 9 to the power of b is equal to 2 to the power of a for some a and b in the naturals. And why do we only have a and b in the naturals? Why isn't a in the integers here? Well, that's because we've got this log to base 2 of 9 is greater than 0. So because log to base 2 of 9 is greater than 0, it follows that we've got this 9 to the power of b equals 2 to the power of a for some a and b in the naturals. So we've not got a in the integers. So since we follows that, right, that we have 2 to the power of a is necessarily even and 9 to the power of b is necessarily odd for all a and b in the naturals, right? That's because we've already proven that if we have even numbers and we do the product of two even numbers, that is even, and the product of two odd numbers is odd. So 2 to the power of a is only ever going to produce even numbers for all a in the naturals, and 9 to the power of b is only ever going to produce odd numbers for all b in the naturals. Therefore, there can't exist any values of a and b for which 2 to the power of a equals 9 to the power of b. So in other words, we've got our contradiction, and hence, therefore, it follows that this logarithm, the log to base 2 of 9, is irrational. And we've proven our statement. We've proven it explicitly and constructively that we found two values, p and q, such that it satisfies our condition above. So that is our finished proof. We put our box in, and that tells us that we've done a constructive proof. So how would a non-constructive proof look? Well, a non-constructive proof is going to go of the following form. So now we're not going to explicitly find values of p and q. We're just going to show that there must exist some values, and what we're actually going to do is we're going to reduce it to two cases. We're going to say it must be either one case or another case. I don't know which one it is, but I know that it must be one of them. So we start by saying p equals q equals the square root of 2. Well, we know that both p and q are irrational here because we know the square root of 2 is irrational. Well, then if we take p to the power of q, then it follows that this number is either rational or irrational. And you might think, well, why did I say that? That's fairly obvious. Well, I also need to use the fact that the square root of 2 is greater than 0. And that's because the exponentiation function on the reals is not closed. So for example, if I take minus 1, which is a real number, and raise it to the power of a half, that doesn't equal a real number. And actually we'll see next week that this is in fact a complex number. So, I can't exponentiate any two real numbers and make sure that I'm still in a real numbers. But because the square root of 2 is positive here, it does follow that the square root of 2 to the power of square root of 2 is a real number. And therefore, because the real numbers can be split up into rational and irrational numbers, it follows that the square root of 2 to the power of square root of 2 must be either rational or irrational. Well, if it's rational, then we're done, right? Because we've got two irrational numbers that we've raised to a power, and we know that we've said that it's rational, therefore we've completed it. But let's consider the other statement. What happens if it's irrational? Well, if it's irrational, then what we can do is define two more numbers. Let's define a and b in the following way, where a is the square root of 2 to the power of square root of 2, and b is the square root of 2. And then let's now look at a to the power of b. Well, what happens if we do a to the power of b? Doing some simple algebra again, we see that we get that is equal to 2, because we've got the square root of 2 to the power of square root of 2 to the power of square root of 2, which is the square root of 2 squared, which in other words is 2, which is a rational number. So in that situation, what have we got now? We've shown that either if p equals q, which equals the square root of 2, either we find that p to the power of q is rational, or we find that if we take p equals the square root of 2 to the power of square root of 2 and q equals the square root of 2, that p to the power of q for that case is rational. We don't know which one because we haven't actually verified which one is the case in which root 2 to the power of root 2 is irrational or irrational. We haven't actually checked that, but we know that it must be one of these cases. It's either one or the other. We haven't explicitly given the values though. So in other words, this is kind of telling us that it's a non-constructive proof because we haven't explicitly found the values of p and q and shown that they satisfy that condition. We've only identified that there must be some values. It must be either this set of values of p and q, either p and q equals the square root of 2, or the other set of values, either p is the square root of 2 to the power of square root of 2, or q, and q is the power equal to the square root of 2. So that's a kind of example of a non-constructive proof in which we haven't found explicit cases in which the predicate is satisfied. So that's now where we're going to conclude the video, and I remind you as always to look at the notes after this video and kind of read around any of the proofs that were discussed in this, as well as attempt any problems in the module handbook. And I also want to say as well what we're going to do next week. Well, next week we're going to actually move away now from this topic of proofs. We've finished now completely with proofs and logic, and we're going to move to a new topic which I kind of briefly mentioned of complex numbers. And then from there on, we're going to actually go on to the actual linear algebra component of the course, which I keep saying is what we're actually doing, but we're not yet there. So thanks again for watching, and I'll see you in the next video.